Okay, so we're going to talk about scope, lambdas, closures, and pure functions today. So let's start off with scope. We have done scope before. Very quickly we covered it. So we have three types of variables we can create. We can say var, say for example a equals a, and if we console.logged it or just put it out, it would output a. And we can also use let and const as well. But let's say we had this in a scope of its own. So what I've done right now is I've created a new block here. And if I was to say, for example, var a equals a, and I had this a over here, it would still output a. And the reason why is because var, it doesn't really care about that code block that we've just created here. So it is still accessible outside of it. But if I change this to let, so these the new variable declarations which were introduced in ES5, I think, will have a new meaning within scope. So let a, and we try to access a, will now, still let us use a. But if I said let a equals b over here, then that would be b. So it's no longer looking at that, it looks immediately at that. If I change this to var, let's see what would happen here. It now changes it to a. So whereas with let, we had let outside here and let over inside the code block. So there was a let within this outside code block which set a to b. And then within this code block, we had a let that set a to a. And when we tried to read a, we got b because this one took precedence. But when we use var instead, var a, we set to b, and then we also set var a within this code block to a. And for now, a is a. So var and let have different rules. So that's a quick look at the differences between var and let. Now let's exclusively work with let and talk purely about what this would do to these when we use different scopes. So for example, if I said let a equals b, and then let's say we have a function inside of here, so function do something, and then we try to print out b, or rather let's put a into here. So I'm going to copy and paste it over here. Now if I try to call a here, much like if we just had the scope or the block, what would happen if I put a here, I try to call a, what are we going to output to the console? What, does anyone have any idea? You can just shout out the answer, even if it's wrong. So what do you think is going to be printed out? B? You think it'll be B if I call A? Okay, well, let's see what would happen. Fascinating. So yes, it actually calls A. Now I think the reason why is because we pardon? We haven't invoked the function, no. So if I was to console.log a here, and let's actually, I think this is to do with one of our previous declarations. Let's say cat, let cat equals b, and we're going to try to output cat. So this is what is the intended output. So we are trying to access cat outside of the function, and it's going to say uncaught reference error. Cat is not defined, because within this outer scope, we're looking for a cat. And outside of here, we haven't got a cat. Inside function, we've declared a cat, but the moment we've gone out of that, cat doesn't exist anymore. If we call, for example, do something, for the briefest time that do something runs, cat exists only within that do something. So when this runs, it's going to jump to here, and say we'll create a cat variable which equals b, and then do nothing with it because we go to the end of the function and cat no longer exists, and we try to access a cat that we can't even touch anyway. So that's a bit about scope. So let's say we had, let's go into our function. So we're not going to look at cat anymore outside of the function, but we know that cat inside the function can be looked at. So we can console.log cat, and we can run do something, and we know that this console.log, when it calls cat, I mean cat's right there inside this function, and if we call do something, it's going to run this. It's going to go inside do something, create a variable called cat which equals b, and then output b. So I can quickly run that, and we get b. Now, how do we access cat outside of b, or do anything with cat outside of b? So we're going to move on slowly into closures. So let's say, for example, I could return cat. So I could say return cat, and that will give me a b. So now when I call do something, it creates a variable called cat which equals b, and then returns that b. So do something returns b. Let's say we had instead declared a function inside a function. So we say function call cat, and we're going to make this return cat, and instead we're going to call cat. Now I do something. What is this do something going to do? So this we have do something creates a cat variable which equals b. We've also defined another function, and then we return this function, that function that we just defined being called. So that function itself returns a cat. So if we call cat, we're returning cat, which is a b. So when we logically go through this, we are going to return a b. So do something should return a b. Great, that's fine. So if I instead of calling call cat, I just returned the handle of the function. So call cat without invoking it. So these brackets, these parentheses, after a function handle name will invoke the function. It will execute the function. But if I don't do that, we are just going to return the function itself. So if I call do something, we're going to return this function which returns cat. We're not actually calling it, we're just returning the function itself. So if I click enter, we should get a function. So we get the function call cat. Now I can say outside the function declaration, I could say, for example, say let the function equal do something. So now the function is the function that we are returning from do something, and we can call this function, so the function, and that should call this function that we defined in do something, which should do print out b. So we got a b here. Now this function here, call cat, we are returning cat. By itself, this function call cat returns cat. Now where on earth is cat? If we look at this function purely outside of everything else, cat is not in the function itself. Where is it looking for cat? It looks for cat outside of itself here. So that's fine. So we know that cat is b. So when we say return cat, we're looking at this cat and we want to return b. So when we say the function equals do something, we return this function that returns cat, which is b. And then we can call this function whenever we want, and it would return b. However, this cat variable, how long does it exist for? If you think about it. So we have this cat variable created in the do something function. And the do something function will execute, it will define this, and then return that function. But the cat variable at the end of it should technically, once it reaches that closing brace, disappear. So this function equals do something. We've invoked do something we've done everything inside of this, and we've just returned this definition. So the function is now this function, and it's returning cat. But what is cat at that point? Well, cat is this variable that was in do something. But what we can call the function is a closure, because this cat has been caught. We've captured it from this do something function's executable environment. So this the context of do something has a variable called cat, and call cat is always going to be looking back at this cat. So even when do something's done, this cat should still exist, because if we're returning cat and cat doesn't exist, we're going to return undefined. So the function here actually keeps this around. And I can actually do something else. Let's create another function. Let's say throw cat out the window. Okay, so now I'm going to do something sneaky. So we know that call cat returns cat, and cat is this thing over here. So we know that this variable, if we touch it, if we do anything with it, this return cat is going to be different. So we can have this other function, which we are also defining, mess up cat. So let's say cat now equals meow. Okay, so if we ever call this function, it's going to change our variable cat to meow instead of b. So let's actually return it so we could use it. So what I'm going to do here is return an object which has both our functions in it. And instead of just calling, so we've gone through object destructuring before. So we know that do something, instead of returning one function, returns two functions. And it's an object with two properties called cat and throw the cat out the window. So they're both functions. And we're going to grab both of those functions from do something. So the function and mess up cat function. So we know that the function returns refers to call cat, and throw cat out the window, mess up cat up function refers to throw cat out the window. So if I call the function, we're going to call cat, and if I call mess up the cat function, we're going to call this throw cat out the window. So if I just call the function right now, we're not even going to look at that. So what would happen if I call the function now? What are we going to print out to the window? Anyone can just shout out an answer. What do you think? Meow. So, okay. You think it would print out the cat? Cat, yeah. It would print out cat. What would cat be at that point in time if I just call the function? So the function refers to call cat, which just returns the cat. We aren't calling this. So if I just call the function, we're going to return cat. We're going to return b. So if I call that, oops, the function is not a. Let's see what exactly is going on here. Do something. The function messed up. Oh, it's because when you object destructure, you should actually call these by their names, their properties. So throw cat out the window. So if I switch this around, so call cat, there, we'll make more sense. So now if I call cat, we're going to make b. We're going to call it b. But I know that we have created this function here, which has access to this cat variable called throw cat out the window. So if I call throw cat out the window, firstly, if I just call throw cat out the window, what on earth is that going to return? What are we going to print out to the console? So I'm just going to throw cat out the window. And, so you think it would print out meow to the console? No, it wouldn't print out meow. Okay, so if I enter, nothing happens. We're not printing anything out. All we are doing is setting cat to meow. We're not returning cat, we're not doing anything, we're not printing it out. So we're just making the cat meow. But knowing that, if we call cat now, and we know that throw cat out the window sets cat to meow, then we call cat, it's no longer going to be b, we can see it's going to be meow. So we can call cat twice. Let's say call cat before we throw it out the window and call cat after we've thrown it out the window. And let's see what it would print out. So console.log. Yes, so what do you think this first one would print out? Yes, and then the second one? Yes. So we print out B and meow. So that's an example of how closures work. So this do something function doesn't refer to any variable outside of it. There is no, for example, let dog equal woof, and then this, and then we're referring to dog inside of that. We're not doing that. So because do something does not refer to anything outside of itself, it's not grabbing any variables outside of its current context, we can call it a basic lambda. So a lambda, in essence, the term lambda, if you ever come across it, a lambda just refers to a function. Just a function. So almost all lambdas, or all functions are lambdas, but not all lambdas are closures. So a closure is a specific type of lambda. So you got the umbrella term lambda, and you got within it a specific type of lambda called a closure. A closure would be this function here. This function is grabbing onto this variable cat. So this is a closure, and do something is a lambda. So, and this is also a lambda. So if you ever see something, if you ever asked, what is this? What is this a closure? You could say, oh, well, yes, this one's a closure because it's grabbing this cat variable, which doesn't quite exist inside of it. So yes, that would be a closure. Now, let's say, for example, so I'm calling this call cat function. I'm calling it twice. Except the first time I call it, I know it's going to be a B. And the second time I call it, I happen to know it's going to be a meow because I know that I've thrown the cat out the window. But if you didn't see that, if you never saw throw cat out the window and you call cat twice, could you say that it would always be B? I mean, we can't really say that because who knows, maybe some unknown person is going to run this command somewhere else. So he might, in some other file, he might throw the cat out the window before we can call cat again. And this call cat function will return us a different thing. So the first time it returns us B, the second time it returns us meow. We can't reliably determine what call cat is going to give us. Call cat, we're calling it with nothing, but it's giving us two different things in two different contexts. So call cat is what we would call an impure function. So there are two types of functions. You can think of functions in two types: pure functions and impure functions. A pure function is if you call a function, it will always return the same thing, no matter. So if you call it with, say, for example, 1, and it returns the value it's been called with, it should always return 1. If you call it with 2, it should always return 2. So you know, no matter where you call this function, if you call it with 1, it will always give you back 1. An impure function, on the other hand, if you call it with 1, it might return dog, or it might return a function, or it might return an object. You don't know what it's going to return. That's why it's impure. You can't determine what it is. So there's a term that we use for this. So a pure function is what we would call deterministic, as in you can determine what it is. An impure function is non-deterministic, and I'm probably spelling it wrong. So if you can determine what it's going to give you, then it's a deterministic function. It's a pure function. It's pure, it's holy, it's great, because it is always going to be the same thing no matter where you call it. And an impure function, well, it's a mess. It could be anything. Who knows? We can't reason with it properly unless we sort of dig through the code and try and logic through it. So it's harder to think about. So a pure function is deterministic. and a pure function is another thing. A pure function should not alter state or influence anything else, or have have any side effects. So if I was to say, so let's get rid of all our cats. So we're going to go straight to a pure example. So let's say we have a function add, and we get two arguments, a and b, and we go return a plus b. This is one of the simplest functions you can ever create, and it is simply always, no matter what we do, return a plus b. So if we console.log, or if we don't even have to console.log, we can just call add 1 and 2, we know it will always give us 3. So if I run that, it should give us 3. So we can say add is pure. Now what happens if I also say add, and then let's say I create another variable here called var delicate stuff equals please don't touch me. We'll set that to happy. Okay, so now we have this variable delicate stuff, which has an object which has a property please don't touch me, which is happy. So let's say we call add, and add's pure at the moment, but secretly inside of add we're going to mess about with this delicate stuff. We're going to make delicate stuff equal null. Okay, so if you call add, you know add, no matter what you call it with, a, b, so 1, 2 will give us 3, 3, 4 will give us 7, 1, 1 will give us 2. So add gives us the same value no matter what the if we put the same arguments in it, it will give us the same value back. However, it has this side effect. So the pure function needs to be two things. A pure function needs to return the same value when given the same arguments. So that is the one of the things it needs to be. And the second one it needs to be is it needs to have no side effects, or at least really so it depends on where you're looking at it. So different languages will think of pure functions in different ways. Some languages only think of pure functions if it has no side effects, and some languages only care if it gives the same value when it's given the same arguments. But really, for the purest thing, you want to make sure that it does both of these things. It gives you the same value when it gives the same arguments, and it isn't going to have a side effect. Because if, for example, delicate stuff equals null, and I want to touch delicate stuff again, I had no idea that this function has just screwed up our state outside. It's messed it up. It's made it null, and we had no idea it was going to have that side effect. So if, for example, I set this to a counter, and I set that to 0, and inside of add, I'm going to be incrementing this counter. Then every time I run add, so let's say add, I call it once. I know it fulfills the first part of the pure function, which is to always give us the same value back when we call it with the same argument. So we know add, every single time we call it, is going to give us a 3, right? So we call add a billion times, it's going to give us 3 a billion times. So that's great. However, we don't know that add also has this side effect, in that no matter where I check it, if I console.log counter here, probably not the best idea to put it there, because now it's jumped up with our 3's. So if I console.log counter here, and I console.log counter here, so let's say counter check counter second time, and check counter first time. So I know I've called add lots of times, and I'm going to check so let's say we're going to check a counter after we called add like 5 times, and we're going to check a counter after we called it another 4 times. We're going to see that counter has changed. In between all these adds, we've changed counter. And so if counter was more than just a number that we're increasing, if counter was like a big object, a big state, which had all sorts of other stuff, and we've been messing it up, we've been adding stuff onto it, we could eventually, after calling add lots of times, create a completely different state than we first thought that we had. So that's why a pure function also should have no side effects, because it's influencing state outside of itself. And if we try to reason with it, what on earth is counter going to be? So let's say we've called add 1 billion times in some other file, and then we try to check counter in our file. What is counter going to be? So we don't know how many times add's been called. Adds influence this counter. So we are mutating state outside of add. So that's what a pure function is. So it needs to be deterministic. Deterministic. There you go. And it should have no side effects. Now, why do we care about pure functions? Well, if this was pure, so now it's pure. If it's pure, and we want to say, for example, call it 1 billion times, we know that because the value is always going to be the same when we give it the same arguments, we could say that this add, 1 and 2, is always going to give us 3. So we can compress add down to a 3. We know that it is essentially always going to be 3. It's a simple function. It does one thing, and we know what the answer is always going to be. So if someone knows what it's going to be, why doesn't he just write 3? So a pure function lends itself to being compressed down to its purest value. When you go to a programming language which is compiled, the compiler itself might look at your functions and determine its purity, and if it is pure, it will optimize it. So rather than computing it, it knows, well, rather than computing it during the runtime, so when you get to the function, it knows beforehand, this function is going to give us 3, I'll just put 3 right in there, because I know this is the value it gives. Sometimes you have to specify that the function is pure for the compiler to even bother doing that, but that is a way to optimize our program, to make it simpler. And we call that, when the program does that, to be, I think the term is referentially transparent. So when this function can also be referred to as its purest value. So if add was 50 and 102, we know that that can be optimized. That is exactly the same as typing out 152. It is exactly the same. So it is referentially transparent. Right. So what other benefits does purity give us? So pure functions are very easy to understand. So if we try to look at a pure function, we will be able to tell exactly what it's going to do, and we don't have to think outside, oh, what is it going to influence? Will this influence thing cause another chain of events which will eventually give us a different value? So with a pure function, we know that this black box is going to operate the same way no matter what. And because of that, we can do some other things. So for example, if I was to make this more complicated. So let's say we're not going to call it add anymore. We're going to make this a very complicated program. So let's call this complicated. And we're going to give it, say, just a single value, and we're going to return something. So with that simple value, let's say we're going to do some complicated things. So let's say we're going to make a for loop, and we're going to say, let's make a standard for loop. I is less than a lot of numbers, then I plus plus, A plus equals I, return A. So we know that in this complicated thing, we are gonna run a for loop which runs like, how much is that? That's a lot. That's that's 100,000. So we're gonna run a for loop that is is gonna iterate through itself 100,000 times and increase A by that. So this A is gonna get really huge and it's gonna take a while, and then we're gonna return A. So we know this is still a pure function. This is pure. So we know if we give it 1, it's going to give us, I don't know, let's say, for example, this will give us 100. If we give it 2, we know, say, for example, it'll give us 200. So with that, bearing in mind that, we can say, rather than doing all this complicated stuff, so if I was to call complicated, and I want to run it on 1, and then I call complicated again later on in my program, and I want to run it on 1, and I want to run it on 1, and I do that several times throughout my program, I don't want to do this super long complicated thing several times, because I know it's always going to give me the same value. What pure functions let us do is do something called memoization. So the term is memoization. So if we know that this value is always the same, what we can do is, so this is sort of being impure now, but we're going to say we'll have a lookup table. Let lookup table equal that. So let's say we know that when we call complicated with A, let's call it once. Let's see what it's going to output us, and let's comment these out so then we don't run it several times. So we're only going to call it once and see what the output actually is, and it might be ginormous. Okay, so this is our output. We know that 1 gives us that. And we don't want to call this several times, or we don't want to run that complicated function several times. If I was to do that, it would go through this for loop, however many times we've called it, and that might take a while. It might take, I don't know. So if we added several zeros, that's going to take a long time every time we call it. So what we can do is, because it's a pure function, we know this output is always going to be the same, we can store the output. So let's say, for example, just before we return A, we're going to store the output. So let's say lookup table, let's say A equals, actually let's say, so let's initial value equals A. So now we're going to grab A before we run it through. Now we're going to store in the lookup table what the initial value is and what its final value is. So if we have this thing, we have this lookup table with the initial value in A, we know that initial value is 1 and A is that ginormous number. So whenever you run this, we are going to set that to that. Initial value is, so it will be 1 and that big number. So after one computation, one run of a complicated function, we have now stored it. We know what the initial argument is, and we know what the value is. And now, instead of running through the function, we can say if lookup table A return lookup table A. So what this will do is, if our lookup table has A inside of it already, we're going to return the value of it. So if we've already run it on 1, so a lookup table has 1 inside of it, then we're going to return that big number. And this will skip our big computation. So if we've done it once, we stored it, and we don't have to run it through the same computation every time. We're just going to be returning immediately that thing that we've already computed. And this saves us a lot of processing. So reasoning with pure functions and understanding what they're going to do, and then we can store their values in a lookup table. So this memoization, pure functions are very good for that. Pure functions are very good for memoization, and you will probably have to use memoization in some huge project later on if you ever want to, say, optimize it. So say your project is starting to chug really slow, you have a lot of things going on, and you have functions which are running again and again, which don't really need to run again and again because they're doing the same computations. You would memorize it. You would save the values that you know are going to be returned, and then just quickly use that lookup table trick to skip the computation. Okay, so that's one good thing from pure functions. Another thing is pure functions lend themselves easily to parallelization. So to be in parallel. So you've probably heard of parallel programming, although we probably haven't done it much, and we are sort of going to be doing it when we look at async and await and stuff. So parallel programming is when you run several processes at the same time. Now, say for example, I want to run, say, crazy function, and I also want to run crazy function, and I just want to run them all at the same time. Oops. Okay, so if I was to call it like that, it would first run crazy function, and it would wait. It would wait and wait and wait and wait until this crazy function's done, and then it's going to call this one, this crazy function. It's going to wait and wait and wait and wait and wait and wait and wait, and then it will call this crazy function. So this crazy function is crazy. It might take 10 years. So we might wait 30 years before we're done with this stuff. But we can run them all. Say if we don't want to do that, we would run them all at the same time. We would run crazy function, and run another crazy function at the same time, and run another crazy function at the same time. By 10 years' time, all 3 crazy functions should be done. We should get them all back at the same time. We don't have to wait 30 years. So if we wait between, after each step, so wait here, then wait here, then wait here, we call that synchronous. We are running it in a single thread. So a synchronous programming. So when it's all one stream of thought. So 1 to 2 to 3 to 4. But parallel programming is when we say we fire off several functions at the same time. So we go 1, and then 1, and then 1, and then later on we're going to combine these all. Let's go down and up and here, and then we get like 3 or something. So parallel programming. So with synchronous programming, we're going to go step by step by step by step by step. With parallel programming, we fire them all at the same time. We let them compute at the same time. Later on, we will probably join them together, and we'll get all the results at the same time. And this, with multi-core computers, our computers can do this. They have multiple processes running at the same time. This can be done on our CPU or even on our GPU. So our CPU, if you bought a computer before, you know the CPU has several cores, for example. So I think sometimes we get 8 cores or 4 cores, a quad-core computer, and a GPU technically would have something like thousands of cores. A GPU is very good for parallel programming, and a CPU, because it has only a couple of cores, is mostly good for a single thread programming. So a CPU is good for this stuff. A GPU, if you have lots of these things running, you can run thousands of them, and the GPU would run all of them at the same time. So that's why if we have a pure function, so tying this back to pure functions, we know the pure function is always going to return the same thing, no matter what the state is, no matter what the state is, the pure function is always going to return the same thing. So we don't care what we're doing around us, if we call this pure function, we can call it anywhere, anytime, anyhow, and it's going to give us the same thing. So why not why wait? If this crazy function is pure, why on earth do we have to wait for it before we call the next one and the next one? Because we know this is always going to give us the same value. It doesn't care what this crazy function, for example, doesn't care what this crazy function did. This crazy function doesn't care what this crazy function did, because they are not influencing state. They're not reading from state. That state doesn't care. It doesn't care about state. They are, as for all intents and purposes, completely separate. So why should we wait? Why not run them in parallel? So if we run a for loop and we run these crazy functions and we fire them off one by one, and we set them to run on threads or different cores, then we can parallelize them. So a pure function lends itself to that. If it's impure, for example, let's say crazy function did something and then the next crazy function had to rely on that, we can't parallelize that, because if this, say, crazy function, so let's actually define crazy function. So crazy function is going to do something crazy. So if we did let state equals, and let's say 50, okay, and now crazy function, it's impure, it's going to look at the state and then increase it by another 50. So if I look at it synchronously in a single thread, crazy function is impure. We have to do it step by step, because the first time I run crazy function, what's it going to do to state? Yes, it adds it by 50. So state's 100. At this point in time, state is 100. Now we run a second crazy function. State is 150, because state's already been mutated by the previous crazy function. And this crazy function, state is now 200. So we know that because of that, we have to run it synchronously in a single thread, in a step-by-step logic, one after another. Because if we didn't do that, it's crazy function. If we run it all at the same time, all three of them, let's say all three of them run at the same time. Let's say we try to parallelize this code, which does this impure stuff. We try to run this impure function at the same time. What's it going to do? So let's say we fired crazy function off 3 times at the same time. They are all going to look at this state, and they're all going to read 50, and they're all going to try to increment state by 50. So state's only going to be incremented from 50 to 100, by 50 to 100, by 50 to 100. And that's all going to happen 3 times, and it's going to happen to the same thing 3 times, and it's going to give us 100 instead of 200. So with it, if that's what you want, then that's fine. But usually you don't want that. So an impure function, it can be parallelized, and if you want it to do what we just talked about, then that's fine. But a pure function, because it doesn't do anything like that, we can just run them off. We don't care about this state. We don't care if state is 50 or 100 or 150. We only care about its value, so we can just fire them off. Now, I have with me an example of this actually happening. So let's say we have a game and we want to create a particle effect. So let's say our game is a window. So let's say we have this window here. Let's create a window. Okay, I'm just going to make a nice window and just presume that this has a border. So let's say we want to make a particle effect. We have like particle here, 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 wherever my mouse cursor is, inside this window here. And we want to make these particles fly across the screen. Okay? Well, let's think about it. What is a particle? Well, let's say a particle is like, let particle equal an object. That's fine. So how many particles of snow are we going to have? Well, we'll have hundreds of these particles. I mean, how many drops of snow do you see in the weather when it's snowing? How much snow is there? It's a lot of snow. If you wanted to count each individual snow, you get like billions. So what happens if you want to run this simulation where you have these particles and they're dropping down? So let's say their position, so one particle of snow over here where the mouse cursor is, its position is, say, x is 50, height is 150. So it's over here. And we want to change that one particle's position. Well, we'll have to change its x and y position. So it goes here, and then here, and then here. And eventually, every time we run our program, we're slowly changing its position. That's great. But we have more than one particle. We have billions of particles, and all of them are going to be doing that exact same thing. Now, if we were to do that synchronously in a single thread where we are running a for loop over our billions of particles, and we know that we're going to make each individual particle move a single step, right? Well, why on earth would the 6 billionth particle care about the position of the 5 billionth particle? Each individual particle, it doesn't care. It can be completely separate. So when we run in this for loop and we're waiting on the 6 billionth particle, and we're still doing the 5 billionth one, we're still changing the 5 billionth particle's position, we're wasting a lot of time. So because we know if we want to change the position of a particle, we change its x and y from one place to another, that's pure. We know if we plus 1 to 1, it equals 2. Plus 1 to 50, it equals 51. That's a pure function, essentially. So we don't have to run it synchronously, we can run it parallel. So rather than running through the loop and then computating on each particle and then doing it all in a single thread, we can go through all the particles and then shoot them all off to compute individually on their own threads. So we get 6 billion particles all having their positions computed at the same time. So rather than one long loop that goes slowly through 6 billion, we do 6 billion instantly, all at the same time. So what's a good place to do that? So on the CPU, we have 8 cores. If we want to do 6 billion things at the same time on 8 cores, or 8 processors, let's say, it's a bit hard to parallelize. If we throw 8 cores, 6 billion threads, it's gonna chug. It's gonna be like, oh, how on earth am I gonna juggle 6 billion things with eight processors? But the GPU, we know the GPU has thousands of threads. So we can throw lots of stuff at the GPU, and the GPU would do it. Have you ever heard of like Bitcoin miners and stuff? They run all this stuff in parallel on the GPU, because the GPU, it runs stuff in parallel, thousands of stuff in parallel. It's much better than the CPU for that if you're running parallel things, because essentially we know objectively this thing's going to be pure. So with my example code, I can show it to you. Let's swip over. Okay. Oops. Right. So this looks a bit complicated at the moment. Okay. So what I created, and I did this about 2015, this is a program which runs on the GPU. So we give this program to a GPU, and the GPU is going to run this exact same program billions of times, but at the same time, rather than on the CPU we do it slowly. So in the CPU, we would have to make a for loop, for example. We have an array of particles, billions of particles, and then we slowly, single-threadedly loop through all of them and run this computation. But if we throw this computation at the GPU and say, right, GPU, do this thing 6 billion times, the GPU would get this thing, and it would run it each individually 6 billion times at the same time. So what this function does, and it does it for snow, this is a snow effect. We give the GPU 2 things. We give it the instance. So the instance would be, for example, the first particle. So particle 1, and then particle 2, and particle 3, particle 4, particle a billion. So the This variable here, GLI instance ID, is a number which just is incrementing for every different particle. So each particle has a unique number. That's great. And we also have an offset. So this is, for example, time. So we know with time, let's say 1 second has passed, so offset is 1. 2 seconds has passed, so offset is 2. 3 seconds have passed, so offset is 3. With these two arguments to this pure function, we know that if we give it, say, an instance of 1 and an offset of 2, this pure function is going to give us a snow particle in some place, somewhere. So, say, for example, over here, whoops, we had the particle over here, and so this particle's number is 1, and the offset is 2. But then in the next loop, the offset is 3. So we know the particle's 1, the offset is 3, so we move it down by that. And the offset is 4, the particle's 1 is 1, so we move it there. And this particle is, say, 6 billion. So 6 billion and the offset is 1, so it moves it there. 6 billion and the offset is 2, so it moves it there. So that's how we have individual particles in different places. Now, let's show you another pure function. So this function here, so it's very useful for you to be able to read functions in other languages, because if, for example, the company you work at might, say, change its framework or change its language, what you're looking at will differ, but the logic is still the same. This is still a function. This function is called rad_uint, and it takes an argument, x, and this curly brace denominates the function's body, and then you got your return statement. It's all very similar to what we've done in JavaScript. And we can see here, x and x equals, so we're doing some computation here. And this extra stuff on the side, this uint stuff, you might not see it in JavaScript, but you'll certainly see it in a strongly typed language or compiled language. These symbols, signifiers, they signify the type of something. A uint, so you know what an integer is, it's a number. A uint is an unsigned integer. So I'm not going to get too far into this, but so integers are 32-bit numbers. And an unsigned integer is, so we know an integer is 32 bits. And we know an integer can be positive or negative. So what is 2 to the power of, say, 31? 2 to the power of 31 is like, it's 2 billion, around that. So with an integer, we have minus 2 to the power of 31 or plus 2 to the power of 31. So that's essentially 32 bits, but one is all the way negative and one is all the way positive. So it's 32 bits, where 31 bits are for the number, and the other bit is for the negative or plus sign. So that's what an integer is. It's the 31 bits are being used for the actual number, and 1 bit is being used for if it's negative or positive. But an unsigned integer doesn't have that negative or positive part. It is purely 32 bits purely for a number. So without the negative or positive part, it's purely positive. So we know instead of 2 billion, it's now 2 to the power of 32, not 2 to the power of 31, so it's 4 billion. So we got all 32 bits, purely numbers, so we know that this function takes in a 32-bit number, which is positive, and returns a 32-bit number, okay? And then we do some bitwise operations. So we know that it's 32 bits. We can mess around with the bits. We can throw the bits around. So if we look at bits, whoops, and here. So bits looks like this. So we get a 1 and a 0 and a 1 and a 0 and a 1 and a 0 and a 1. And if we wanted to mess around with it, say we wanted to shift all these bits over to the left, then we would get, say, we'd lose that one and we'll pop another one over there. We've moved everything to the left. So we lost the first one over here and we've added another one to the end. And if we kept doing that, let's say we moved it again. So this is well off topic, by the way. Okay. So essentially, what this function does is it takes an argument and it does some crazy stuff and it returns a random number or a pseudo-random number. We know that no matter what this gives us, it's always going to give us the same thing. And because it's so similar to JavaScript, we can test it. We can actually use it here. So let's show you how to convert this to JavaScript. So I'm going to get all of this, delete it, and plop it here, and demonstrate to you how you would convert something to JavaScript, and also demonstrate to you why this function is pure, even though it looks so weird. So the first thing we're going to do is we don't have to specify anything with ints. We don't have to specify this u part. So we know this function is pure. And what does a pure function do? A pure function is two things. Could you tell me what those two things are?
Same all the time.
Yes, that's one thing. Yes, that's the second thing. So pure function is the same no matter what the value is, and it has no side effects. So if I call this var uint with 1, it's going to give me a number. But if I call it again, and again, and again, and again, it's going to give me the same number. If I call it with 2, and the intended idea is that it gives me a completely different number, it's a pseudo-random number, it's going to give us something completely different. If I give it a 0, it's going to give me something completely different again. If I give it 4, it's going to give us something completely different. But the idea is, if I give it a 4 again, it gives us the same thing. This is a demonstration of pure functions. Pure functions, even if the result is completely different to the value, the result is always the same no matter what the value is, if the value is the same. So this crazy stuff, no matter what it is, it's still pure. In its definition, this function is definitively pure. Okay? And I think I can end there. But essentially, what happens is we use this pure function to give us something that's random with our instance number, so say 6 billion, and the offset, so the time. And then we use that to give us random positions across the screen. And it's random across the screen, but because this increments slowly, it's going to slowly move the particle down the screen, even though its position is completely random. That's the intended idea. So, yes. That's pure and impure functions, and we covered scope and closures a bit, and talked about lambdas and stuff. So yeah, so just if you want to look up stuff, look up determinism, look up referential transparency. Probably have to, Google will spell this correctly for you. Look up memoization, that's really useful. I suppose side effects. But these things, I think they're good terms to look up. So if you're ever confused about stuff, or if you want to impress someone, you would look up these terms and you would know these methods and what the definitions of pure functions are and stuff. It's very useful. Okay? Yeah.
With your functions from line 2 to 3 to 8, is that like a lambda, right?
Yes, yeah, yes. You can call this a lambda. So we know that lambdas, everything, all functions are lambdas. So we could say, so there are many ways to define a function. Const var equals this part over here, this arrow part. This is a function. So you see this part here, the part I've highlighted, that's the function part. That's a function. And we can call that a lambda. If we didn't have this part here, we just look at this, just look at that, that's a function. And it's a function that, say, return A. And we can call that. So let's comment out everything else, or just delete it. So we have this function here that just returns A. It's going to complain a bit. Okay. I think if we want to just straight up. So this part here, that's a function. This function, we haven't named it. We haven't given it a name. No. So if we wanted to call that, we would have a hard time calling it. It's an anonymous function. Anonymous function meaning a function without name. So that's another term you can look up, anonymous functions. But we're calling it. So right now we have this function. We've enclosed it with a parentheses, and we can call it, and it returns a. So it didn't have a reference to a, but it figured that out for me. So that's a function. We can say function equal, this is a function, and we call that a lambda. Yeah, that's a function.
I'll ask you more question offline.
Mm-hmm. Okay, so essentially, sometimes you would only hear that lambdas are only anonymous functions, but really, in most languages, they would think of lambdas as every function. So it comes from lambda calculus. So you would see some programming languages. So you should look up lambda calculus, or just lambda in the context of programming, a calculus. So for example, a programming language like Haskell, for example, is what we call a functional programming language. Functional programming language. In that it uses only pure functions. So everything in that programming language is pure. And if you try to do something that's impure, well, it's hard to do that. So Haskell is very focused on purity. And that's good, because with that you can parallelize it. If we know that this function here is always going to give us the same output, we can think of it with I've talked about it before, with referential transparency. So we know that function A returns A. So we can just think of it as A. So Haskell can lazily think of that as A. It's something called lazy evaluation. So these are terms you can look up later, so I'm not going to go into them now because it's a very big topic, but yeah.